So today I want to give you a few more clues as to the direction I'm going with my ether model. Now, every time I go to make this video, I get a little bogged down because there are a lot of aspects to this model and that's very difficult to explain using words. And so um, here are many of the concepts that are associated with the ether model. The Bose-Einstein condensate, which I've talked about before. Of course, magnetism is involved, as well as electrostatics, isopotentials, electron-positron pairs. The ferrocell plays a role, as I will talk about later. We need to deal with Maxwell's equations, fluid dynamics, and of course, the fractal paradigm is the main reason why I'm doing any of this. So my hypothesis is that the ether exists, that there is an ether, and the ether is the medium for the propagation of light, but it is actually much more than that. The ether that I envision is the foundation with which everything else emerges, and so it's not just the medium for the propagation of light, but it is the source with which everything that we observe emerges. So I'd like to start with the Bose-Einstein condensate, which is a vortex. So within the context of the Bose-Einstein condensate, we observe vortex lattice structures that appear when under certain conditions of the BEC. So I'm just going to call it a BEC because it's very difficult to say Bose-Einstein condensate over and over and over again. Okay, so the BEC is a state of matter where supercooled particles act like one big superparticle, governed by the same wave function. So basically what they're saying, so if you take a material and you supercool it, okay, if you take a material, a gas of some atom, and you cool it down and you cool it down and you cool it down till nearly absolute zero, what happens is it begins to behave as if it is one particle, one super particle, and not a whole bunch of particles. And that's what it means to when they say it's governed by the same wave function. It's governed by one wave function instead of, or by a more simple wave function than a bunch of particles would be considered. And so at the very base, so this is the foundation. So the hypothesis that I'm proposing is that the universe began in the thermodynamically opposite of what the Big Bang. So the Big Bang supposedly started at the hottest you could possibly imagine, and I believe the universe started as the coldest you could possibly imagine. And so when you take these gases and you supercool them, basically they become sort of like a blank slate. Okay, so when you take, so here in the experiments that were done here, what they did was they cooled down a material, and when it's super, super, super cold, it becomes basically a blank slate. It's got no structure. It is basically just one wave function, one very simple wave function, and that is what you would see. There would be no structures. And so what they do is they try to spin up. So in this state, in this BEC state, it is very resistant to change. Okay, so if it has a lot of inertia, because inertia, I define inertia as the resistance to change, it is very resistant to change. And so what they do is they trap these atoms in a thin layer, in a magnetic trap, and then they try to spin it. Okay, and so the BEC completely is resistant to these changes. It does not want to spin. So instead of spinning, what it does is it spins up these tiny quantized vortices. Okay, and so as you spin up the BEC, you get one vortex, one quantized vortex, then you get two quantized vortices, then you get 3, 4, 5, and so on. And each time, so these vortices appear instantaneously. These, you can think of these as phase transitions. So it's not like it's slowly spinning up these vortices and then they, they spin up. They basically just appear basically instantaneously at a certain angular momentum that they are trying to induce in the BEC. Okay, so as it spins up, you get one quantized vortex, two quantized vortices, three quantized vortices, and so on, up until the point where you have a field of quantized vortices. And so this is how I envision the ether behaving. So in the model I'm proposing, the universe started off with 0 vortices, and then as it spun up, you got 1 vortex structure, 2 vortex structures, and so on, until the universe was filled with these vortex structures. And this is the background with which this is the medium for the propagation of light. So the medium for the propagation of light isn't the background, it's not the background, it is the lattice. Okay, this is a lattice structure. Okay, the vortex lattice structure that forms over time as you spin up a BEC. And so here you will see, so I sort of am modeling these vortices as a yin-yang, because the yin-yang has, a spin. This schematic has a spin built into it, and so this yin-yang is spinning counterclockwise. So you can imagine if you curl your fingers in the direction of rotation, your thumb is going to point to what I would consider to be the North Pole. So you can consider these vortices as dipole moments. Okay, anything that spins has a dipole moment. And so this is one dipole moment, and then we have 2, and then we have 3, etc. And as I showed you in previous video with the experiments that Yonel Dinu did, is when you have say 2 cylinders in a fluid spinning in the same direction, so these 2 would be spinning in the same direction, these 2 cylinders, these 2 objects will repel. And so this explains why in the Bose-Einstein condensates we know that these are spinning vortex structures. This explains why they would be repelling from each other. Now keep in mind, this BEC is a 2-dimensional experiment. This experiment is done in 2D. So this is a 2D extrapolation of what might be going on in 3D. And so don't take this too literally as what would happen in 3D, but you get the idea that you have these vortices which are spinning and they are repelling each other, and this explains why you get this, this lattice structure. So in the absence of matter, before matter was even formed, I believe that the universe began at the super cold BEC temperature of absolute 0. And as it spun up, and why did it spin up? I do not know, but we also don't know why the Big Bang happened. And so as the universe spun up, you get these vortex pairs forming, and in the absence of matter, they form this crystalline structure. And so when I wrote my paper, A Medium for the Propagation of Light Revisited, I proposed that the medium for the propagation of light was a space filled with these vortex structures that we can draw schematically as dipole moments. Okay, and so we all know that when you take 2 charges, so here's a positive charge and a negative charge, when you bring them close to each other, when there's charge separation, you get a field that looks like this. And there's no explanation for why there is a field, but my explanation is that the universe is filled with it's a polarizable medium. Okay, so here's a paper that I found just randomly, polarizable vacuum representation of general relativity. Okay, and here he says that there is, so this paper shows that the vacuum acts as a polarizable medium by virtue of induced dipole moments resulting from the excitation of the virtual electron-positron pairs. And so in my paper, A Medium for the Propagation of Light, I model a vacuum as electron-positron pairs. So I say this figure depicts how a medium of electron-positron pairs might self-organize in the presence of ions or charges within the medium. Okay, the image on the left shows unlike charges in the medium, and the image on the right shows the like charges. So this is a negative charge and a negative charge in the medium. So when you place a charge in the medium, okay, the dipole moments from the Bose-Einstein condensate align themselves in such a way to surround the charges. It's basically trying to surround and neutralize these unpaired charges. So you can think of these as paired charges, and these are unpaired charges, and it is trying to surround and neutralize these charges, and this is how they would self-organize in the presence of a positive and negative charge, and in the presence of a negative and a negative charge. You could also think of the medium of the propagation of light being filled with something akin to iron filings, or more interestingly, you could think of it as a ferrofluid. Okay, so in a ferrofluid, especially when in the context of the ferrocell, okay, in the ferrocell, what you do is you take a few drops of the ferrofluid and you drop it into a medium like baby oil, which acts as a medium with which the ferrofluid sits in and becomes like a colloid solution. Okay, so what I'm going to do is I'm going to show you a quick video. So let's pretend that the ether is a ferrofluid, and so and here we've got a 0.01 millimeter. This represents 0.01 millimeters in the video I'm going to show you. And so here we're going to start with, okay, so when there is no magnet present, when there's no other dipole moment in the field, okay, the ferrofluid is just a bunch of dots. Okay, these aren't oriented anywhere. They are basically, I'm going to show you, they are basically these, analogous to the vortices in the BEC. Okay, so they're just a bunch of dots. And it's interesting in the ferrofluid because let me go back to the video, the dots are not all the same size, they're all different sizes, so they clump almost in a fractal pattern. You've got big clumps and little clumps, and when a magnet is brought into the field of view, what happens is they become polarized. So they clump together. Let me just go back a tiny bit. Let's look at that again. Okay, so the magnet comes into the field of view, and what happens is they stretch out and they align into these needle-like formations. And so you can also see there's kind of a fractal pattern where you have big ones and little ones, and you can also see that they're not clumping together. These are like tiny iron filings. Okay, they're no different than actual iron filings. Okay, they're very similar to the iron filings, and so they basically line up with the magnetic field of the magnet that's being placed into the field of view. And so this is kind of how I see the medium for the propagation of light. When you take, in this case, this is a ferrofluid, so it reacts to a magnetic dipole. Okay, so these are aligning to the magnetic dipole, and you get this pattern. And so as you move the magnet around, you get these magnetic moments. So these in themselves are magnetic moments, and they are reacting to the motion of the magnetic field. So let's just go through here a little bit. So, and here you can actually see them placing the magnet up here. Okay, and let's just go a little further. Okay, so as he moves the magnet around, you can see these dipole moments. You can see these iron filings. They're basically mini iron filings, and they are moving around. As he moves the magnet around, they move around with the magnet. And so when you take the magnet away, it goes back to the what we saw at the beginning, where there are no magnetic moments, there's no orientation, they're just dots, and they are repelled by each other. In the case of the ferrofluid, they're repelled by each other because the nanoparticles they have a surface, they are coated with a surfactant, which causes them to repel. In the case of the Bose-Einstein condensate, they are repelling because the dipole moments, they're not magnetic moments, they're dipole moments, are spinning in the same direction, and that causes them to repel. So it is an analogy. This is the ferrofluid is a loose analogy, but I think it's a very good analogy for what I'm trying to describe in terms of the ether and the medium for the propagation of light. So next, what I want to show you is that there are actually two flavors of dipole moments. There's the electric dipole moment, and there's the magnetic dipole moment. Okay, and both of these dipole moments are governed by two of Maxwell's equations. So I'm just going to quickly show you here. These are the four Maxwell equations. We've got Gauss's law of electrostatics, which is this equation here. We've got Gauss's law of magnetism, which is this equation here. And these are the only two we're going to deal with today, so we don't have to worry about these today. So we've got the divergence of the electric field is equal to the charge density, and the divergence of the magnetic field is equal to 0. Okay, so what does that mean? I know I've talked about it before, but I think it's a good idea to understand what this means. Now, in terms of electric field, we know that a positive electric field has a diverging field, okay, where the field appears to emanate, the field lines appear to emanate from the positive charge. And I think this is just convention. I don't think there's anything actually emerging from it, but there might be in my model. And so you've got a diverging field, and you've got the negative charge being depicted as a converging field. Okay, so we need to understand what divergence and convergence are in order to understand Maxwell's equations. Okay, so in Maxwell's equations, we've got the divergence of the electric field is basically non-zero if there is a charge present. And so what this means, is if I draw a circle somewhere in the field, okay, there is somewhere in this field of view, where the divergence is not equal to 0. So divergence of 0 means, okay, if I drew a circle here, this is a surface, you can think of this as a surface, okay, there are just as many arrows going in as coming out. There are just as many arrows coming out as going in. So right here, the divergence of this region of space is 0, okay, because you've got arrows going in and arrows going out. But when you put the circle right over the charge, then you have arrows coming out and you don't have any arrows going in. So this is the divergence. The divergence is non-zero here because you have arrows going out and no arrows going in. And of course, if I place the circle here, you're going to have arrows going in and no arrows going out. And so that is the meaning of this equation here. Basically, it's saying that the divergence of the electric field is not 0 everywhere, but it is 0 somewhere. It's 0 here, it's 0 here, it's 0 here. It's just not 0 when you're looking right on top of the charge. And so the divergence of electric field is highly dependent on the charge density. So if there's charges in the field, and these charges have charge separation, then you're going to have the divergence of any region of space is going to be non-zero somewhere, okay, and in particular surrounding these charges. Okay, so now we have the magnetic field. There's a magnetic dipole moment, but more importantly, there's a magnetic field. And in the magnetic field, the divergence of B is equal to 0 everywhere. Okay, so if I put a circle here, let's go to this one here. This is actually easier to see with a ring magnet. So I'm going to show it with a ring magnet because here you've got these two, the north and south pole, they're kind of overlapping, they're touching each other. And so it's hard to see what's going on inside here. And so with a ring magnet, you've got this condition here where you have a current going through the current ring. This X means into the page, and this dot means out of the page. And so the current is going into the page and out of the page. And if you curl your fingers in the direction that the current is going in this current ring, of course, you have to use your imagination to imagine that this is a ring. But if you curl your fingers in the direction that the current is flowing in this ring, then your thumb is going to point in the direction of the North Pole. So in this depiction here, in this schematic here, the North Pole is up here. Okay, so it's basically like this, and the South Pole is down here. And so using the ring magnet, you can see that the divergence of the field is always zero. And what that means is it doesn't matter where you put a circle in this image, you're going to have field lines going in and field lines coming out. You're going to have vectors going in and vectors going out. And so even in the very middle here, or even let's say we move this over here, you're going to have arrows going in and arrows going out. And you're not going to have the condition where you have only arrows going in and only arrows going out in the case of the electric field. And so that is the difference between the electric field and the magnetic field. In the magnetic field, there is no place in the field that has where the vectors only diverge or only converge. But when you look at it closely, there's really not much difference between the electric field and the magnetic field. In terms of a dipole, in terms of having two charges or a north and a south pole, if you don't look inside this region, you get basically the same pattern. Okay, so if I could block out this region, you wouldn't be able to tell the difference between an electric field and a magnetic field. Okay, so what we're going to do something really interesting. We're going to have a look at the software that I showed you quite some time ago. So here what we have is the software. Let me shut this down here. Okay, so we have the software such that you can place an electric charge anywhere in this field of view, and you can see what the field lines would look like in various configurations. So here you can clearly see that the positive charge always has the arrows pointing out, and the negative charge always has arrows pointing in. And so I'm going to, I'm going to place the positive charge here and the negative charge, say here. Okay, and here you can see that the negative charge, so this is the dipole, like I showed you in this diagram here, okay, where you have around the positive charge, you have the arrows always going out, and here you have always the arrows coming in, okay. And so let me go back to this here. So we see with the negative charge, you have the arrows pointing towards the negative charge, and here you have the arrows pointing out of the positive charge. So what I'm going to show you, I'm going to move this down. Okay, I'm going to move this down closer to this charge. You still see that here the arrows are pointing away from this charge, and the arrow is pointing to this charge. But now what I'm going to do is I'm going to move this so that it's touching this here. So when the positive and negative charges are very close together, when they're bound, I'm going to call this a bounding condition. When they're bound, then you have the condition where the field looks identical now to a magnetic field. Okay, so now we have something that looks more like this, where we have the arrows where the divergence of B is 0 everywhere. Okay, so let's have a look at that again. We've got a condition here where you've got the field coming out of the positive charge and going around and into the negative charge. and you can see that that there is no arrow in between that is pointing towards the charge. So my hypothesis is that the only difference between an electric charge and electric dipole moment and a magnetic dipole moment is in a magnetic dipole moment, the charges are bound. They're bound to a system, they're bound to each other. They're bound to a system is basically what I'm trying to say. So they are bound to a system such as an atom. And so when the positive and negative charges are bound within the atom, what you have is a magnetic dipole moment, something that looks more like a magnetic dipole moment than an electric dipole moment. Okay, so this would be an electric dipole moment. You can actually see the dipole structure out here, and which looks, of course, like the electric dipole moment in this image here. Okay, it's very similar. And the magnetic dipole moment looks like this. Now you can see as I bring the charges together, the magnetic dipole moment doesn't extend nearly as far as the electric dipole moment. Okay, the electric dipole moment, the field extends much further than the magnetic dipole moment. So this is a very weak, extends very weakly, and so what you have to do to strengthen up the magnetic dipole moment is to put a whole bunch of them together. So if you bind a whole bunch of these magnetic dipole moments together into a body, such as a magnet, then you are going to get a much stronger magnetic field. So to me, it seems like there's not actually that much difference between an electric dipole moment and a magnetic dipole moment. The only difference appears to be that in the electric dipole moment, there is charge separation, and in the magnetic dipole moment, the charges are bound to each other somehow, i.e. in the atom. So when they're bound to each other inside the atom, they appear as magnetic dipole moments, and when they are not bound to an atom, like say in a molecule, like in a water molecule, there is charge separation, so they appear more like an electric dipole moment. So in terms of the electron-positron pairs that I'm talking about that make up the medium of the propagation of light, okay, so here's what happens when you take the one of the charges. So when they're close to each other, you have a magnetic dipole moment, and when they're right on top of each other, okay, when they're right on top of each other, there is no field. Okay, there is no field. The field disappears. Also, we know that when electrons and positrons come together, that they annihilate. And so my line of thinking is that they don't actually annihilate. What happens is when they completely bind to each other, they fall back into the medium. Okay, they fall back into the medium. And in the absence of matter, they basically kind of do nothing. Okay, there is no field. So in the case of the Bose-Einstein condensate before matter ever appeared in the field of view, okay, now we've got matter in the field of view because we have a positive and negative charge. Okay, so when matter appears in the field of view, then these charges separate a little bit and they become dipole moments, and then these in of themselves would surround these dipole moments at a different scale. And so you can imagine that these are very, very, very tiny, very, in the, quantum scale, at the Planck scale, tiny, tiny, tiny dipole moments. They are literally the ferrofluid that I talk about here. Okay, what happens when a charge and or a magnet comes into the field of view? So this works for both charges and for magnetism. Is the particles become slightly charge separated, and then they align with the magnetic field of the larger magnet that comes in the field of view. So you can think of this in terms of small magnets in the field of view of a large magnet. And so if we go back to the ferrofluid, okay, here we have these tiny dipole moments, these tiny nanoscale that have become polarized in the presence of the magnet. So the magnet is very large, and that these magnetic moments are in the field of view of they're close to the magnet that the person is holding right here. So there's the large magnet here, there's the ferrofluid here, and as they move the magnet around, it is affecting the dipole moments in this field of view here. And so basically we're talking about small dipole moments in the vicinity of large dipole moments. Okay, so that's what we're talking about here. In the case of here, what we have is, you can imagine that these arrows are the dipole moments of the ether. So now this is the ether, although you have to imagine that these are infinitesimally small. They're very, very small. They're at the scale of Planck scale, and that these are extremely large. This would be an electron and a positron, or this could be an electron and a proton. These are going to be much larger than the scale of the dipole moments in the ether that I'm imagining. Okay, so we are talking about small dipole moments in the vicinity of large dipole moments. Okay, this is how the small dipole moments behave in the vicinity of a large dipole moment. So there's a scaling, there has to be a scaling difference for this kind of to work. Okay, so you can imagine that. This is the medium for the propagation of light. It is made of dipole moments. You can imagine that these are very, very, very small compared to the particles that are in the vicinity, in the region, in the field of view. And then these dipole moments, they become polarized. This is a polarizable medium, and they become polarized, and then they surround the positive and negative charges to form the field patterns that we are all very familiar with. So given the fact that an electric dipole moment is not that different than a magnetic dipole moment, as we see here. So we've got an electric dipole moment where the divergence of the field is non-zero, and then here we have the condition where the divergence of the field is zero everywhere. Okay, I would be inclined, so these two laws, so the divergence of the electric field is not zero when there's charge separation. This is called Gauss's law of electrostatics. And the divergence of B equals zero is when the charges are bound to each other, as I show here. Okay, I would be inclined to rename them, because you all know, if you watch my videos, you know that I'm not a big fan of naming laws after people. I might be inclined to name this law the law of unbound charges, or the law of charge separation, charges that aren't bound to each other. And I would be inclined to name this one the law of bound charges. So when they are bound to each other, when they are so close together that they no longer have a divergence, you can't see the divergence, then I would be inclined to maybe call this the law of bound charges. Okay. So when we're talking about dipole moments and the ether, okay, and the ether as a polarizable medium, what we're talking about is a large dipole moment in the vicinity of, small dipole moments in the vicinity of a large dipole moment. So when you take, let's say, a magnet, which is a giant dipole moment, at least a magnet in this configuration is. Basically what we're talking about is the field itself. So now I want you to imagine that these little magnets, don't think of them as magnets, think of them as dipole moments that are polarized by the presence of the large dipole moment. When a large dipole moment comes in the field of a bunch of small dipole moments, those small dipole moments line up along the field lines of in the field of view. Okay, so this is not unlike what we see with iron filings. Iron filings are a polarizable material, and when you place a magnet in the field that contains a bunch of iron filings, you see this pattern. And the interesting thing I want to show you with this pattern is that the material seems to kind of spread out. It doesn't clump together. You would think that if these all became magnets, that they would just clump together and form a giant clump, but that's not what happened. We see a lot of separation going on between so it forms these stringy things, just like we saw in the ferrofluid. In the ferrofluid, we see that when you bring the magnet into the field of view, it forms these needle-like structures, these sort of bifurcating structures. Of course, you can see these similar structures in the iron filings as well. So this is ubiquitous of scale. So at the nanoscale, it is doing this, and at the large scale of the iron filings, it's also doing this. Okay, so here's what's happening. Okay, when you bring a large dipole moment in the vicinity of small dipole moments, what happens is the small dipole moments align themselves as follows. So you can, if you want to think of them as magnets, you can see that the North Pole is touching the South Pole, the North Pole is touching the South Pole. So they are going to self-organize into this pattern. And you can see that this pattern is going to cause these strings to spread out because you have North Poles next to North Pole, which repel. Okay, South next to South that repel. And so you've got these strings, these lines. I can show you next to the iron filings. You see that they follow the lines of the magnetic field lines. But what I also want to point out is that the dielectric inertial planes of the dipole moments tend to want to line up parallel to, if you can call it parallel to, because this is a curve, they want to line up with the isopotential lines. Okay, these are the equal potential lines. These are the lines, these curves of equal potential, and you can see that these magnets are aligning themselves to be orthogonal to, exactly orthogonal to these curved surfaces here. And so this explains why the iron filings, and also why the ferrofluid, okay, why they kind of are forming these lines, and also why they are not attracted to each other, because they're tending to line up orthogonal to the isopotentials, and they're also lining up such that the norths are aligned with the norths and the souths are aligned with the souths, and this explains why they are not attracted to, why they don't clump together. They kind of tend to want to spread out. Okay, we've got repulsion between these lines going on in this situation here. And of course, everything that I'm saying that is going on here is also going on in the medium for the propagation of light, as I am trying to describe in this paper here, the medium for the propagation of light. So the field pattern that we see around positive and negative charges is happening because the ether is a polarizable medium. Okay, the ether is a polarizable medium, not unlike iron filings and or the nanoparticles of the ferrofluid, only it is at a much smaller scale. So you can imagine that the ferrofluid is at a much smaller scale than the iron filings, and the medium for the propagation of light is at a much smaller scale. to the nanoparticles of the ferrofluid, and this is where the fractal paradigm comes in. Okay, the universe, this is why the universe is fractally scalable, because this process is fractally scalable, depends on the scale of the medium, and also we're talking about small dipole moments in the vicinity of large dipole moments. Okay, so you can imagine that the dipole moments of the ether being at the Planck scale are super, super small, but they would be aligning with the magnetic field, and that's why we can feel a magnetic field, and why, I think it was Faraday that talked about them having kind of a stringy like consistency, because they would align almost exactly like they do in the iron filings. So to get further clarity on this, what I did was I asked ChatGPT a bunch of questions. Now I know, like, I'm basically going to tell you, don't trust ChatGPT. Use it as a tool. If you're asking it questions about information, you may get some confusing results. So you have to be very careful how you ask it the questions. Okay, so here are a bunch of questions I asked ChatGPT in regard to this line of thinking. Okay, so can an electron be, because we're talking about small magnets in the vicinity of large magnets, or small dipole moments in the vicinity of large dipole moments. So what is considered a dipole moment? Okay, so I asked the question, can the electron be considered a magnet? And it said, yes, an electron can be considered a magnetic system, because it possesses an intrinsic magnetic moment associated with its spin. So this intrinsic magnetic moment is a fundamental property of some subatomic particles. Okay, so anything that has spin, and so I want to go back to the Bose-Einstein condensate, the BEC example, because here these little vortices, we have vortices, and these vortices are spinning, and they would be considered to be a magnet because they have a dipole moment because they're spinning. Okay, so then I asked, can the proton be considered a magnet? Yes, a proton can be considered a magnetic system, because it possesses an intrinsic magnetic moment associated with its spin, just like electrons. This intrinsic magnetic moment is fundamental property of all subatomic particles. Okay, so then here's the interesting part. And so can the hydrogen atom be considered a magnet? Yes, a hydrogen atom can be considered a magnetic system, because it has a magnetic moment associated with its intrinsic spin of the electron. The magnetic moment of the hydrogen atom arises from the orbital motion of the electron and its intrinsic spin. Okay, so so let's keep going. Can electric dipole moments, such as water, interact with a magnetic field? Okay, so the idea is, can do all dipole moments interact with magnetic fields, including electric dipole moments? So yes, electric dipole moments, including those found in molecules like water, can interact with a magnetic field. This interaction between an electric dipole moment and a magnetic field is described by a phenomenon known as magnetic dipole-dipole interaction, or the magnetic dipole moment's interaction with a magnetic field. When an electric dipole moment is placed in a magnetic field, it experiences a torque that tends to align the dipole with the magnetic field. The torque is proportional to the strength of the magnetic field and the magnitude of the electric dipole moment and the angle between the dipole moment of the magnetic field. So basically, the electric dipole moment behaves exactly like a magnetic dipole moment. Okay, and just go to here. So an electric dipole moment behaves exactly as a magnetic dipole moment in the vicinity of a large magnet. So in the vicinity of a magnetic field, and the assumption here is that the magnetic field is, much bigger than the dipole moments that are interacting with the field. Okay, so now I want to go back to the hydrogen atom here. So can the hydrogen atom be considered a magnet? Okay, and it said yes. Okay, so here what I'm envisioning is that the hydrogen atom is a dipole moment. Okay, you can say the nucleus, we could say the proton. We know the proton is much larger in terms of mass than the electron, and so if we consider the atom as the nucleus of the atom, the proton as the large magnetic moment, and the electrons as the small magnetic moment, then we might be able to make sense of the orbitals. Okay, so when you look at the electron orbitals, what I found is that, and we want to look at the isopotentials now. Okay, so the magnetic isopotentials are the equal potentials. These are the diagrams that I produced using Michael Snyder's software for generating isopotentials. And so what I discovered was that the patterns of the magnetic orbitals, okay, so that's where the word orbital came in when we're talking about the hydrogen atom. We're talking about the orbital motion of the electron. Okay, so the orbitals of the small magnets in the vicinity, the electrons, small dipole moments in the vicinity of the proton, large dipole moment, behave very similar to, behave very similar to the isopotential that I generated using Michael Snyder software. So you can see the 1s orbital is very similar to when I am looking at a single pole. So when we look at the magnet just from one direction, we get the very similar to what the 1s orbital looks like. And then the 2p orbital, where we have two, so we have a positive and negative charge, or you could say a north and a south pole bound within the atom. Okay, so this would be considered a magnetic dipole moment instead of an electric dipole moment, according to my hypothesis. Then what you would end up with is the isopotential. So the electron orbitals are matching the patterns, are matching the isopotential patterns of this configuration. And then when you take a, positive and negative, which would be a north, when I took a north and a south and a south and a north and put them in this configuration, I got the isopotentials, the electron orbital. So this is where the electrons could be within this region. This is where the small dipole moments would be relative to the large dipole moments. And here we have the 4s orbitals match very nicely with the with what I find in the isopotentials. Okay, and then we go to the next iteration. So this is the 1s orbital, and this is the 2s orbital. And when I do the set up the magnets to be analogous to what's going on in these situations here, I see that the isopotentials match exactly with the isopotential patterns match exactly with the orbital patterns. Okay, and so my feeling is that maybe we're just not describing things correctly, or that this connection here is more intrinsic than what we've previously been led to believe. Okay, here's another configuration that matches perfectly. We get the shapes, these exact shapes of the isopotentials match the electron orbitals. And so in this configuration, the isopotentials correspond to the locations that the electrons would comfortably sit, right, depending on where it is within the atom. Okay, so this is something I made a video on a while back, but it sort of came up while I was making this video. Okay, so and the isopotentials are exactly orthogonal to the magnetic fields. Okay, just to remind you that the isopotentials, okay, the magnetic field lines are exactly orthogonal to the isopotential. So these are not two different fields. these are just two different ways of looking at the magnetic field or of the dipole moments. I don't even want to call them magnetic fields because the electric field, the isopotential for the electric field is exactly the same as the isopotential for the magnetic field. So looking at isopotentials alone, you cannot tell the difference between okay, let me just go to my software here. Okay, so here I have the isopotentials. I drew the isopotentials of of an electric field, and they look exactly the same as the isopotential of the magnetic field. And I think I have some diagrams here. Let's see, where did I put that? No, I don't. But okay, so these are the isopotentials of the electric field. And oh yeah, there it is. These are the isopotentials of the electric field, and these are the isopotentials of the magnetic field. And you can see that the shapes of these lines are the same. So you're looking at equal potential, isopotential alone, you cannot tell the difference between an electric field and the magnetic field. The only way you can tell the difference, okay, the only way you can tell the difference is by looking closely at the divergence of the field itself. Okay, so when the charges, let me go to this one here. Okay, when the charges are not bound to each other, you have the electric field, and when the charges are bound to each other, okay, when the charges are bound to each other, then you have the magnetic field. And that's why I believe that when the electron and when the two charges, the proton and the electron, are bound within the atom, they're behaving more like a magnetic field. And when they are not bound, then they behave more like an electric field. Okay. And so, and also to reiterate, I want to reiterate the fact that an electric field and a magnetic field they are not that much different from each other. Okay. But when the charges are bound to each other, they're going to behave more like a magnetic field. And then in order to get a strong magnetic field, you have to bring a whole bunch of them together to get so the more dipole moments you have bound within an object, within a physical object like a magnet, the stronger the magnetic field is going to be. And that's why, and the more they're aligned, so the better they're aligned. So if these were not aligned very well, then the field would become weaker. But also, the more dipole moments you have packed together in a magnet, in a material object, the stronger the field is going to be. And of course, that is what we experience. That is what we know. And that's why I believe that when the electron and when the two charges, the proton and the electron, are bound within the atom, they're behaving more like a magnetic field. And when they are not bound, then they behave more like an electric field. Okay. And so, and also to reiterate, I want to reiterate the fact that an electric field and a magnetic field they are not that much different from each other. Okay, but when the charges are bound to each other, they're going to behave more like a magnetic field. And then in order to get a strong magnetic field, you have to bring a whole bunch of them together to get so the more dipole moments you have bound within an object, within a physical object like a magnet, the stronger the magnetic field is going to be. And that's why, and the more they're aligned, so the better they're aligned. So if these were not aligned very well, then the field would become weaker. But also, the more dipole moments you have packed together in a magnet, in a material object, the stronger the field is going to be. And of course, that is what we experience. That is what we know.